Now that we have a pretty good understanding of the basics of machine learning and are starting to understand the conceptual underpinnings of a number of different possible ways in which to approach a predictive analysis, we're going to walk through an example here. It's going to be a pretty simple example, but I want you to get an understanding of how decisions are made when doing machine learning and predictive analyses. And at the end of this, I'll introduce the idea of overfitting, and we'll talk about how to address overfitting in the next video. So the question we're going to be using for this example is what you see here. Can we build a model that distinguishes a house in New York from a house in San Francisco? And when we're in a classroom, I ask students to discuss this with their neighbor and think about it. So before we proceed, I encourage you to pause and think about all the different ways in which you could build a model to distinguish a house in New York from a house in San Francisco. So one approach would be that we could take a whole bunch of images, some from San Francisco, some from New York, train a model, maybe a neural net, and then use that to predict for future images. So that would be a deep learning approach. But in this example, we're going to take a more supervised learning approach where we have the underlying features and information about which observations came from San Francisco and which came from New York. So this is where I would ask students to consider what they know about each of these cities and determine what features they might think are important. So if you have ideas, feel free to continue on. If not, I encourage you to pause it, think about it here. What students often come up with would be that maybe they want to say, look at cost per square foot. So something that people know is that New York and San Fran are both expensive cities, but maybe also are aware of the fact that in New York, the cost per square foot is likely higher than in San Fran, because in New York, you get very small apartments that are very expensive. Another thing you might be able to use are the type of the house, because the facade might differ, the material used, the roof used, the climates are different between the two. All of these features are possible ways in which we could, if we knew that information about a house, distinguish whether or not a house was from New York or from San Francisco. So this process is what we're going to be doing here. With one of the first things that we want to think about here is a single feature. So when we're talking about distinguishing New York from San Fran, this is a classification task, right? Our outcome is categorical. It's not continuous. So we're going to use classification approaches that we talked about in previous videos. One thing you might think of, aside from cost per square foot, is that San Francisco is hilly. Elevation could be a helpful feature. Any houses at elevation you would likely think came from San Francisco. And what we see here on the right are the data from our data set. So for all of these images, San Francisco will be in green and any house is going to be in blue. So each row, each horizontal line is a different house. And what we're plotting here is elevation. So the highest house is at 744 feet of elevation in the San Francisco data set, with the tallest New York home being at 239 feet. So we can see that here, homes at about 73 meters should be classified as San Francisco homes, right? Anything above here is very much likely to be San Francisco. Below that, we don't necessarily know, right? It could be in New York or it could be in San Fran. So this is where we start adding additional features to our model for classification. Elevation on its own is not enough. So what we can start to look at is the relationship of elevation to another feature like price per square foot. So if elevation is on the y-axis and price per square foot is on the x-axis, we can see that those homes that are low elevation but more expensive per square foot are likely to be blue dots, New York. Those that are high elevation are likely to be San Fran. Now we're still not able to distinguish down here. But this is the idea of a classification model, where not just looking at, a scatter plot of two different features, but we start to use these decision points and additional features to build our classifier. And the idea is for each of these features, we can draw boundaries so that if a house falls in the green box area, we would likely say it's San Fran. If it falls in the blue box, it's New York. And then down here, we're not really sure. Statistical learning is the process of figuring out how to best draw these boxes to best improve our calculations and our classifications. And the idea here is you do this for a myriad of features. So maybe you're looking at elevation, year built, bathrooms, bedrooms, price, square foot, price per square foot. Here is a scatter plot matrix where we're just plotting each house and the relationship between those two. And the patterns are clear, but the boundaries or delineation are not obvious, right? We see that there's this shape here when we're looking at the relationship between price and square foot, that there are New York homes up here and those at lower price per square foot down at the bottom, but we don't really know what the best place to make this decision boundary is. That is the process of where machine learning comes in. Figuring out which features to include and where to draw those decision boundaries for each of these features when, say, building a decision tree, which is what we're going to do here, is a machine learning method for a classification task. So before this, it was really exploratory data analysis. We were taking our features, understanding them, looking at some plots. The process of figuring out which features to include where in our model and which decision points to use for each of those features is the process of building a decision tree. And the process here is using machine learning approaches. So finding better boundaries. I guess 73 before said, no, somewhere around here would be a good boundary, but how do we improve on that guess? Well, this histogram here shows the frequency of homes by elevation, where 73 meters is the highest home in New York, where most then have lower elevations. The process in machine learning of splitting your data at these boundaries is where we call a fork. The fork is the place where the decision is made, and this splits into branches based on that value. The value that splits the branches is the split point. So if we want to figure out the best point to figure out how to get the best separation between San Francisco and New York, where the homes to the left of the split point are categorized differently than the houses to the right, we can do that. And a decision tree really uses these if-then statements to define patterns in the data. So for example, splitting at 73 meters would determine that all of the houses above 73 meters are San Francisco. So we would get all of those right, as none of them would be New York. But it doesn't do a great job at the lower end. 111 of the houses to the left of our split point would be New York, and 92 would be San Francisco. So we would say everything to the left is New York, everything to the right is San Fran, and if we did that, we would only be 63% correct. So the idea is that we have a whole bunch of false negatives. We would call these New York, but they would be truly San Francisco. And there are trade-offs. No split point here on this single feature is going to be perfect, but we want to find the one that sets us best up so that when we make additional decisions, we're able to better distinguish San Fran and New York homes from one another. If we were to split to capture every home in San Francisco, we would have to set the elevation split point at 0 feet, which means that all of our houses would wind up in the San Fran category. Now, it would get all of our San Fran houses right, but all of those that are New York and being classified as San Francisco would be false positives. So we want to balance the true positives and the true negatives and minimize our false positives and false negatives. So we have to figure out what the best split point is. So here the best split point is at 91.9 feet. At this point, up at the top, most of them are San Fran, but of course we accept some New York homes here. And down here, most are New York, but we accept some San Fran. And now our percent correct is 82%. So the best split point aims for branches that are as homogeneous, as pure as possible, knowing that we have to accept some impurities. And the process is then figuring out the split point for all of our features. The idea of recursion is determining additional split points. And we do this through repetition or recursion, or going through one, going through to the next, figuring out and adjusting each of the split points as we go until we can maximize our correctness. So what this means when we're talking about a decision tree is we take all of our data to start in our training data set. And we first split by elevation at the split point the computer or the model determines best. And now we're looking for homogeneity, but we see that we have to accept some imperfect predictions at this first split point. And then we build our tree. So elevation was the first feature we split on this right hand. Now we split on price, so that those that are more expensive end up on the right and those that are less expensive on the left. We split by price per square foot, and we continue building this tree based on the data and the features we have. so that towards the end, all of our houses fall into some category where we then classify them based on being from San Fran or New York. Adding these additional layers to our decision tree, we ultimately get to a 96% accuracy. We see that the vast majority are homogeneous, but we do still have places where we have some houses that are being misclassified. Now, we could add branches until our model is 100% accurate. In this model, we've added additional features so that every leaf of our tree is homogeneous. It's either green or it's blue. So we've built this model so that it perfectly predicts every single house using the features in our model. Now, the idea is that we don't just build this model so that it works on our training data. We can see how it performs on our training data, but the idea is we want to see how it performs on our test data, data that the model didn't see when building the decision tree. So the first thing we do is run our training data through it. And we said that we trained it to 100% accuracy so that all 111 New York homes are predicted to be from New York and all 139 San Fran homes are from San Fran. Now, we then send our test set through, take every single house, send it down our tree, and figure out what decision is made for the test data. When we do this, we see that there is some misclassification. Some San Fran homes are reported to be from New York, and some New York homes are reported to be from San Fran. So in our training data, we have 100% accuracy, but that accuracy drops in our test set. In this data that wasn't used to train the model, we only have 89.7% accuracy. Ideally, the tree should perform similarly on both known and unknown data. Your training data set will often have slightly higher accuracy than your test data set, but you don't want your training data set to be way different than your test data set. And the errors we see here are due to overfitting. Fitting every single detail in the training data leads to a tree that modeled unimportant features that didn't generalize when we used our test data set. It did not allow for similar accuracy in our new data. So if you're training your training data set to 100% accuracy, you're likely overfitting your model. So it's okay to accept some lower level of training accuracy to increase your generalizability of your data and to avoid overfitting your model. What we saw here is that machine learning identifies patterns using statistical learning, and it identifies the boundaries in your data set, and you can use it to make predictions. We here used a decision tree, which is one way to use if-then statements to generalize and make a classifier. And when we did this, we showed that if you fit every single detail of the model in your training data set, you will often overfit your model. And this happens when some boundaries are based on distinctions that don't make a difference, right? It works in your training data set, but it doesn't matter in the general data you would use this model on. You can often see if a model overfits by having test data flow through the model and seeing how accurate you are from there. This here was an example of a general approach to how to make a decision tree and what decisions go into this. In the next video, we're going to talk about how to deal with this issue of overfitting.